So first thing is I woke this morning and discovered that Randall Munro had decided that our enterprise is important, which is always nice to hear. And second quick thing is that the workshop tonight, is it 7? Is that right? Did we say? I actually don't know what it says on the schedule.
Yes,
it says 7 on the schedule, so that'll be back here. Actually, we might move over into the lounge if it's more comfortable for group stuff, because this is not easy to sort of cluster in here. But so the what? Yeah, how many people show up? We might go here. We might go over into that little lounge over there. So we'll see. All right. So we left off on Friday, having decided that friction and forces matter, and today I'm going to move on to talking about some of the frameworks we can use to understand some of what I showed on Friday. All right, so quick recap. A lot of the experiments you'll see, although not all of them, are done on an Airtable. These are 2D, and if you didn't get enough time to play with the demo, you can come up and play some more with it. We have a flat array of disks. We can take those disks and extract the contact forces, and we can do lots and lots of stuff with them. Okay, and so this is being facilitated by the fact that we have a solution to the photoelastic inversion problem. And so a lot of what we're doing is taking images, figuring out what the contact forces are. Okay, and this is a pseudo image generated from those contact forces, which illustrates that we've gotten them pretty close to right. Okay, and those of you who've been asking me questions about how you actually make all this stuff, there's a review article out a month or two ago where we even list which companies you can order the stuff from. So. All right. So the first thing I want to do is look at tools from network science. And I think there was some of this a little bit earlier in the school that I wasn't here for. It was also 2 weeks ago. So stop me if I'm doing stuff that's too repetitive from that. What we want to do is take our collection of grains that we have determined somehow. Okay, and we're going to write this as a network. Let me get some more colors of chalk. For this. All right, so we're going to write this as a network. So the particles will be the nodes. Sometimes people call these vertices on a graph. And then we'll connect them by, so the contacts and perhaps even the forces, we'll get to that in a minute, will be the edges. Okay, and if we're just talking about contacts, that's what gives you a binary network. Just yes, no. Okay, versus a weighted network. Okay, and this could either be by, for instance, the magnitude of the force, or the tangential force, or the normal force, as you decide to pick it. Okay, so the tool for this case, there's an adjacency matrix. This is an adjacency matrix Aij that equals 0 for no and 1 for yes. Those are contacts. Very easy. Okay, and for the weighted case, Wij is equal 0 for no and a value representing the force depending on what you want. So the force at the contact. Okay, and it could be any any of these by the user's choice. Okay. So what does this look like? Oops. So here's an example of a particle packing. This is actually just taken as a photograph, not really an experiment. These are sitting on a table. You look at the nodes, those are the centers. You look at the edges. You can write, and what we're doing is basically writing this as a graph. Okay? The adjacency matrix, so A would look like this. Black is every time there's a yes. White is every time there's a no. If they're weighted, then the grayscale shifts according to that weight. Okay, and there will be a review paper out on arXiv soon. This is what I was supposed to be working on this weekend. But the Arapahoe Glacier Trail was lovely. All right. So if we take this from one of the pictures, and this is actually not from the frictionless airfit, this is from a vertical slot where we're doing the sound propagation. You can take one of these images. You can go through all the finding of the forces. You can write down the weighted adjacency matrix, and you get something like this that comes out of it. So this blue, the thickness of the bars, tells you the weights. All right, questions about that? Clear? All right, so this is work that I've been doing with collaboration with people in network science. And they have, people who study voting records in Congress and social networks on Facebook and epidemiological networks and transportation networks. And all these folks have a whole bunch of tools. And they're easy to get access to. Right? So I'm not somebody who writes any of these tools. I'm a user of them. And they're not difficult to use. So some resources. So Mark Newman has a great book. This is very easy to understand. So it's an intro to networks book. It's long and thorough. If you want to get algorithms, the place I get mine is called NetWiki. And it's the Applied Mathematicians, amass.unc.edu. And then hopefully soon we'll have this. So these sort of things reduced to talking about just particulate systems we'll have up on arXiv hopefully soon. All right, so starting from the particle scale. So looking at the nodes. Okay, so what are some tools from these toolboxes that are useful? So one is something called the degree, but the network scientists call the degree K. Okay, and so for the ice particle, so this is going to be the ice particle. Whenever I'm doing stuff up here that's about a single particle, we'll have a subscript I. Okay, and you're just going to sum over all of its the whole. So this is the number of particles. Okay, it's also the size of the n by n matrix. Okay. Aij. Sorry, there should be a J here. Okay. So you sum down one of those columns or one of those rows in what we looked at up here. Okay. So you sum on one of these. Okay. So this is a local measure, right? There's also a global version, right, where you actually write this slightly differently. Global version, which is the average K, it's 1 over m. Now we'll sum over all the individual ones. Okay, and this would just be the average contact number, okay, in the jamming sense. Okay, so just slightly different notation. Okay. We have weighted information, so you can look at node strength. Okay, I'm going to call that sigma, and that's actually summing the same thing, summing up, but this time the weighted adjacency matrix. Okay. So you're going to include the information about how how strong the force is, not just that it's there or not. Okay. Another useful measure at the node scale is something called the clustering coefficient. Right? So looking at these triangles that form, okay, and for instance, this is a node that's very densely connected to triangles. This is a node that's not, right? Okay, and you can see that this is probably related to the packing fraction also. Right? There's a lot of geographic constraints, geometric constraints that are involved here. Okay, so you can look at something like the number of closed triangles. And I'm not going to write this mathematically, just to sort of a sense of the kind of things they have. So how many closed triangles are at a point versus the number of, let's see, nodes with 3 edges. Right? So there's all sorts of sort of node scale measures that you can do. Okay. So that's at the particle scale, right? We have Boltzmann. Okay. How do I do this? I guess I'll go over here. Right. Okay. So we want to look at the force chain scale. So actually, let me write here. This is the particle scale. Okay. And the force chain scale, or what the network science people call paths. Okay. So for instance, you can calculate things like Dij, the shortest number of hops from node I to node J. Now, this is not completely trivial, right, to calculate. Okay, so this is why it's sometimes useful to have toolboxes where you can download these things. So the shortest number of hops, or if you want to do a weighted version, okay, you can also do that. Weighted version. You can count the total weight. And that gets even trickier to calculate. Because it might be that a longer number of hops actually accumulates less weight. Right? So they get non-trivial to calculate. So there's some useful numbers here, like network efficiency that you can calculate. Right? So how does it make good use of short hops? Like you think in a travel network, how easy is it to get, how easy is it to get from between other places? Right? So network efficiency E, right? Right? Is you're going to sum, not going to yourself, right? The more efficient you are, the shorter those distances are. Right? So these are convenient measures. All right. This is the first one I'm actually going to use to show you something. So the notion of centrality. Okay. So these are all answering how many paths go through node I. So these all ask these sorts of questions. So i.e., if the centrality is high, it's a major intersection. Lots and lots of routes have to go through. This is the Chicagos and Houstons of the airplane network, right? So one of them is something called closeness centrality. And there's different definitions. There's different kinds of centrality. People have come up with different measures, right? So closeness centrality is very clearly related to the network efficiency. Only if the sum is in the denominator instead of taking. Okay. So the larger this is, the longer this distance is, the less central you are, right? It's not many things go through you. Okay. The one I'm going to look at is something called betweenness centrality. Okay. And this is a little bit complicated. All right. So you want to know, if I want to go from, so I'm at node I, and I want to go from J to M, 2 other nodes. Does that need to go through me, or can it go some other route? Right, so this gets at this question in a really obvious way. Okay, so what we're going to sum over is the number of paths that go through I versus the number of paths that don't. Okay, and we want to sum over, again, this is paths from J to M. Yeah, I can write bigger. Yes, I will do that. Okay, so let me tell you why this matters. Okay, so I'll stop here and show you some data. All right, so all right, so we're starting on this. We're looking at networks on different scales. So we've talked about particles, and we've talked about whether or not paths have to go through certain points. So this is data from a real network. Okay, and this red point up there is something that lots and lots of paths have to go to, okay, to get from the left side of the graph to the right side of the graph. All right, so here's an example where we might want to use this. Okay. So we had talked about counting constraints and forces, right? In this example here on the left, there's 5 contact forces, so there's 10 values need to solve for, but there's only 9 degrees of freedom, right? 2 translational, 1 rotational, okay? And so you're free to pick one of those forces. There's an extra force left over, right? So what this means is that if you set the packing, right, and I don't know why this is not showing. Huh, very strange. All right. Whoops, sorry about that. Let's go back. Very weird. Huh, this is not showing the picture. I don't know why not. Let's just. There we go. All right. So this is what's known as the force network ensemble. If you fix the configuration of particles, whether it's ordered or disordered, and you still try to make sure you have torque and force balance, there's many possible networks of forces that would solve that problem, right? So this is an ensemble, okay? And you can ask, how does, the history of how you generated the forces affect that ensemble? You can ask just, if you do the same experiment over and over again, do you get the same answer every time? The answer is no. Okay. And this has to do with counting the valid states, right? Now, there's an infinite number of these, because if I have one solution, right, it's in torque and force balance, what happens if I multiply it by 1.7? Still valid. 1.6, still valid. So there's an infinite number of these, right? All right. Yeah?
Do you consider the torque balance?
So in this case, they weren't, because these were frictionless particles. Okay, but we have friction, and so we do need to consider torque balance. Yeah, but the statement holds for both cases. Yeah.
If you multiply,
yeah.
the constraint that you have is the total impulse.
Right.
So you can't.
So you can't multiply, but the point is just, okay, so yes. So there's going to be boundary constraints at some point that are imposed, right? So it doesn't, so
Without boundary constraint,
there are no solutions. Excellent point. Okay. All right. So, but just to give an idea of just how large this space is. Okay. So here's a subset of 1,000 solutions, and I showed you guys this on Friday, right? And you guys pointed out correctly that this is an extremely popular particle, right? Okay, we do 1,000 of these, and this guy almost always seems to be one of the ones that's on the force chain, okay? And this guy seems to be supremely unpopular, right? Okay, so why is this? So network science actually, I think, answers this, okay? So this is work that my postdoc Jonathan Colmer is doing. So if we take that packing, so the upper left, we've actually coded this strength that I wrote in the board. Okay? So the brighter the particle is, the higher the strength is, averaged over the whole ensemble. Okay? So the red particle here is the guy that you guys identified as being extremely popular. Okay? However, you also notice, let's watch the movie again, some particles are reliably popular, and some particles are unreliably popular. Right? So this guy here is not reliable. Sometimes he's in, sometimes he's out. Sometimes he's strong, sometimes he's weak. Right? So Jonathan calls this flakiness. Right? So there's particles that are strong, there's particles that are flaky. So the important ones are the ones that are both strong and not flaky. Right? I'm not, so what the way this is done is there's a wall that you're not seeing that can be, it's actually at the top of this picture, that moves out by a tiny fraction of a particle diameter, so the forces are all gone, and then it goes back in. Okay, so the wall goes out and the wall goes back in, far enough out that the forces are all relieved, but not so far out that they rearrange the contact network. So this is an ensemble over a fixed binary contact network, or approximately fixed. Okay, they can be 0, but not a fixed. A fixed binary contact network, but not a fixed weighted network. Yeah.
Are you sure you sampled the whole ensemble?
No, I'm not at all. It's what the experiment samples, right? And so this is a place where we talked about advantages and disadvantages of simulations versus experiments. Someone doing simulations, of course, can use clever sampling techniques to alleviate that. I can't, right? I can only do the experiment. Yeah. So no, we don't. Okay, so no, although this is still early data. And this is actually a small system. We have some more data on a 1,000-particle system that we're working on analyzing. Okay, so this is I think it's 30 or 32 particles. I can't count them. All right, so here's so the upper left was the strength. Okay, so the mean pressure of the ensemble. The upper right is the flakiness, so the standard deviation of that. Okay, and so the importance, okay, is we want to say, and so actually this is rescaled in some other units, so it's okay. So we want to sort of say if it's both strong and it's not flaky, right? That's what we're going to call importance. So this is the guy you guys pointed out. He's super important. Okay, then we just go and using the binary network. So no information about the forces, just information about who is whose neighbor. Okay? We calculate the centrality. Okay? And what you get is that the ones that are high on this centrality measure are the popular important particles. Okay? And this does hold for a larger system as well. Okay? So we can make a scatter plot, and I don't have that. But if you make a scatter plot of the centrality versus the importance, we get something like that. Okay, and it's not a function of depth, at least to first. Yeah, Georgios. I can come back to the same what? So the force distribution. We can calculate as well, and that's not defined. I mean, you can do that in a single packing, but I don't want to look at a force distribution on 30 particles. That's not a meaningful thing, right? But this does converge. There is a force distribution this converges to. Yeah. Is that what you mean? Just how much force there is, but they're not the same. They're not the same each time, right? They're not the same each time. So every snapshot of this has a different force distribution. It's only 30 particles, right?
The force that you impose is always the same?
The force, no, the volume. So I'm imposing volume here.
Oh.
I'm imposing volume here. No. Yeah. So that turns out this is an experimental detail where it's easier.
The average force
is also fluctuating. Yes, it's also fluctuating. Yeah. So the average force is also fluctuating. Is that what you meant? No. It can't. Yeah, but you can't talk about a distribution on 30 samples. On 1,000, it starts to look more constant from sample to sample. But 1,000 is also not a very large number, right? Yeah, and I didn't put them in the slideshow, but I'd be happy to show them to you afterwards. We have them, right? And they actually they're statistically stationary. There's with an exception that because this is a real experiment, every so often, let's say this guy got too much force. What do you think happens to him? So he doesn't actually break. They're strong enough, but he can pop out of the 2D system. Right? So we can get catastrophic failure, right? Which means we have to end that experiment. Right? So there are caveats to it as well. All right. Yeah.
The write-down panel, we can see the 4 bright circles, but on the left panel, the brightest they are the same one, the larger one, but the other
are not quite as bright.
Kind of dark.
Yeah, they're not quite bright. So that's why there's scatter.
Yeah, how strong is the correlation?
Can you get back to me in a month?
Yeah.
This is an ongoing experiment. This is an ongoing experiment. But there is scatter. So I can't tell you this is definitely going to be. I mean, I might have voted this one may actually be this one may be the equal value. So I couldn't have told you that this was going to be more important than that one. But I can bet on which ones are the most important, right? And so, but this makes sense as a physical, that if I'm trying to transmit force from one boundary to the other, right, the particles that have the most paths going through them are most likely to have the force chain going through them, right? And this is just using the normal. This is actually, I think this is using the magnitude of the pressure, so not even a vector quantity, right? And so there's fine tuning that you can imagine doing. We haven't done that yet. But this is robust over a bunch of different packings and over the large ones and the small ones at least. OK. Yeah?
It just occurred to me that that small particle in the center that has very high centrality might be artificially higher than that large particle because it's actually more central to the packing.
Yeah, and so this is the question of how you detangle geographic location from the geometry of it. And like I said, this is an ongoing project. I can't answer all of these questions because we just haven't finished exploring the data. Yeah. All right. OK, so let's see, where are we here? All right, so this is now, so we've done the particle scale. We've done the force chain scale. Okay. And now I want to look at a mesoscale. So communities of particles or force chains. So one of the things that we saw on Friday was that the sound waves were largely traveling along the force chains, right, and ignoring other parts of it. So not all parts of the pack were participating in anything you might do to it. Okay. So we'd like to identify, okay, so regions of a packing that are strongly connected to each other. Okay? i.e., what you see by eye. Right? So when you look at one of these, go back up to the top. Right, so what's striking when you look at one of these pictures is that you can identify by eye the force chains, right? Okay, when you're playing with the demo, you say, those are the force chains, right? So what do we mean when we see those are the force chains? Like, so why do we ignore some of the other stuff, okay? And there are people who have done this by hard thresholding, for instance, saying, we're going to cut off all particles below the mean or something. But some particles below the mean may actually be stabilizing other force chains and could be important, right? So we'd like some way of extracting the important force chain network, okay, without having to make the decision ourselves, doing it in some optimized, unbiased way. Okay. So this is what we're going to use. So network science has techniques which are called community detection. And I'm just going to talk about one technique for doing that that I have used. There are other ones out there. There's a huge community of people doing this. And so community detection, I'm going to look for subsets. Okay, these are the communities of particles who are more strongly connected to each other than to particles outside their community, right? So if you wanted to think about this in the Facebook sense, if you were to plot your network of Facebook connections, you would see your friends from high school all know each other, right? Your friends from college all know each other. Your friends from grad school all know each other, but there's not many connections between those groups, right? Okay, and there are outliers, right? And so, so these are algorithms that are set up to, if you give it one of these adjacency matrices, they extract community 1, community 2, community 3, and when you look at it, you can go, oh, high school, college, grad school, right? Okay, so they have some physical meaning that can be detected once you do the calculation. Okay, so like I said, this is where we discover that I don't use these boards at my university. I'm completely perplexed about how to optimize them. Guess the lights don't work on this side. Okay. So this problem is actually NP hard. You can't actually solve it. You have to actually write an algorithm that goes through and optimizes something and does the best it can, but you can't guarantee you got the best solution. Okay. So these are algorithms where you tend to run them a bunch of times and check that what you're getting is consistent. All right. So the one that I use, I'll try to start writing our optimizes a quantity called the modularity Q. Okay. And what it tests is the following. Okay. So it's going to sum over all pairs of particles, okay, where I actually does not equal j. Okay. The weighted adjacency metrics compared with some null model. Okay, so this is the weighted adjacency matrix we define. This is a null model. Okay, and it's only going to make this comparison if the two particles are in the same community. So this is if they're in the same community. And this is a resolution parameter, which I'll come to a little more in a minute. But basically, it's a knob that tells you, do you want to be finding lots of communities, or do you want to be finding a few communities? Right? So how much do you want to break the network up into communities? Okay. So this is more or less, this is fewer or more communities. Okay. And this is what you're comparing to. Okay. So if two particles are in the same community, right, they should do better than the null model and Q grows, right? And if they aren't in the same community, you don't care, right? So you start by randomizing assignment to communities, and there's a heuristic algorithm, and we use the one that's on this NetWiki at UNC, okay, that Peter Muka is a main author of. And you just runs, and it has a heuristic algorithm. It says, well, would it be better for me to move this particle in or out of the community? Okay, and if the answer is no, it doesn't. If the answer is yes, it does, right? And it steps through smartly until you get a set of community assignments. Okay. It turns out, however, this choice of null model is incredibly important. So early on when we were doing this work, we used the same null model that almost everyone uses, which is the Newman-Girvin null model, which basically says that any node can be randomly connected to any other node. Does that make sense in a packing of particles? No, because you can only be connected to the ones who are your neighbors. Okay? So we use something called a geographic null model. a geographic null model, okay, where we say our best guess is that it's the average force times the binary adjacency matrix, right? You want to do better than that, right? So more strongly connected than the mean or less strongly connected than the mean, okay? And this says, so that this gives an interpretation that gamma about 1 means you're comparing above or below the mean. It's a very natural, physically inspired choice. Okay. So let me show you what happens if you pick a good null model and a bad null model. All right, so the left is what happens if we use the obvious thing, which is Newman-Girvin, because everyone uses it. You get communities that are compact, right? It's a bunch of particles that are all geographically near each other, but don't sort of look like the force chains, and that's what we were after. If you're smarter and you pick something that is more driven by the actual properties of the system, you get communities that now start to look chain-like. Okay? And the colors here are arbitrary. I'll start showing some ones later on where they're coded by the strain. Okay? But these aren't. Okay? So it matters that you pick a good null model. In the first picture, they all are. I'm trying to think if they always all are. Yes, they always all are. They're different communities. Yeah, we used some sort of random number generator to generate the colors, and it possibly wasn't as random as it could have been. Yeah. Right. Possibly a poor choice of color scheme. All right. So let's talk about this parameter gamma. Okay. So we want something. So I'm after something that gives me the force chains, right? So that I can compare to sound propagation or to buckling under shear or some other physical process. So I want the force chain backbone. Okay, so I have to pick gamma to do a good job of that. Okay. So what is something that is nicely, tells me I've got a force chain? So here's two options. Okay, so we've used both of these on different times. They both work fine. So one is that we compare, if I pick two nodes, how far do I have to hop to get from one to the other versus how far apart are they actually geographically? So those 2 points up at the top there, you have to hop quite a way, but they're actually pretty close to each other. That's because it's a very branchy structure, right? Something that's compact or linear, the hop distance and the geographic distance are pretty much the same thing. Okay? So we can look at a ratio of those two things, and the larger that ratio is, the more branchy the structure is. The other method we've used is to take particle communities that have been detected, shrink wrap them. This is called the convex hull, right? And the ratio of how much volume the particles take up compared to how much the hull takes up. Again, the more the shrink wrap is compared to the particles, the more branchy it is. So either of these are useful for determining a good resolution parameter that gives you good force chains. Okay? And it turns out not to matter a whole lot which one you pick. Okay, so here's just a graph of as we change the resolution parameter, and this is from our sound propagation data, you get the gap factor, so how the ratio of the distances, to be nice and large, anywhere around 1, which is what we expected. Okay? And there's some example images of force chain structures that are picked out in that vicinity. So it's quite sensitive to the resolution parameter. And depending on what you're trying to do with it, you might want to pick different values. Right? But you have this control in the algorithm. All right, so once you have a set of communities, you can characterize them. Right? We can look at some of these other properties we've talked about. We can look at the average strength of the community. Right? We can look at the average degree in that community. We can look at the average sizes of the communities. We can look at distributions of those values. Okay? And these are sensitive to how you made your packing. Right? So if you made your packing by shear, or you made it in a computer, or you made it in an experiment, or you made it under various circumstances, these network statistics are not the same. Okay, they can distinguish among them. So here's just a quick case study. So this is a set of, we took data from the lab where we're compressing particles. They have friction, they have real walls, they have friction, right? And compared them to some simulations that Lisa Manning did, where they had periodic boundary conditions, they had no friction, they had all that list that we made on Friday. So these are not the same system, okay? And not surprisingly, So the red ones are taken from the numerical packings. The black ones are taken from the laboratory. We made them as close as possible, except for all that long list of differences. And they don't have the same network statistics, right? And so what this gives you as ways to say is you've all looked at pictures from simulations from experiments. They don't look the same, right? The forced networks don't look the same. But how do you quantify that? How do you say, well, well, they look, clumpier, or they look, I don't know, bunchier, right? So this is a way that you can then quantify that. That if you've done two different things, how are they the same? How are they different? Do they vary in size? In branchiness? You can actually quantify that. And I think that's a nice way to get beyond just looking at things by eye and saying they don't look the same. It gives you a toolbox for characterizing things as a function of some parameter in your experiment that you may care about. Function of shear, function of friction, et cetera. Yeah, Mike?
Is there any overlap between those?
Actually, I think technically they do with their noses. Yeah, I can't remember, actually. They're not very... Yeah, the point of this isn't to determine whether they overlap. It's just to show that these separate features.
And were all of the ones generated in the laboratory generated by the same
protocol?
Yeah.
So both of these encompass things where we changed the confining pressure.
Okay.
That's all we did. And so I think pressure goes along, as you might expect, this axis. Right? Yeah. So things make sense like that. Mm-hmm.
The numerical stuff, is that just soft spheres?
It's soft spheres, yeah. Mm-hmm. Yep. And these particles are fairly soft. Right. So there's not much information to be gained from this graph except that these two populations are obviously different. Right. It's not meant to be any deeper than that. Something's the same. We made them the same number of particles, the same stiffness to deformation ratio. We kept as many things we could the same, right? Except that they differed on that list that we put up on the board on Friday, right? In all the ways that simulations usually differ from experiments, right? And yet we try to draw comparisons between the two very often, right? And we know they aren't the same, right? And this tells you some of the ways in which they aren't the same, okay? That the branchiness of them is different and things like that. All right. So now we want to move from static packings to ones where there's some sort of dynamics, right? So you have snapshots. Okay, so maybe it's because something is impacting it and the forces are changing, or you're cranking up the pressure, or you're subjecting it to strain, right? Whatever it is you decide to do to your packing. Okay? But you want to introduce time into this, right? Or step, or pressure, something where you have a series of images. Okay? So to do that, you need for example, increasing compression, which is the example we used, right? So let's say I've got a set of networks, right? And I could find the network here, and the network here, and the network here, and the network here. And I could find communities in each of these. But I'd like my community to say these particles actually stayed as a community over time, or over compression. So we need to have ability to have a third dimension, okay, that encompasses that. Okay, and these are what are called multi-layer networks. There's techniques for that. Okay, and what you need, in addition to this resolution parameter, is some degree of stickiness between the layers, right? So if this particle here is the same literal particle, because I did particle tracking, right? How much weight should I give it staying in the same community, right? And if I set that to be 0, then these are completely independent determinations. Okay? If I start cranking up this omega, it says that if you're the same particle, you should try to tend to be in the same community, right? And I can play with that knob. Okay? And there's little theoretical guidance as to what that value should be. Okay? So we did the experiment. Okay? So here's a set of data where we moved the walls in. Okay? So we compacted the packing, and you can see the force network evolving, right? So it's getting stronger, right? There's more and more chains, okay? The color coding here is by the value of this value Q, okay? And these are individual snapshots if we found communities separately in each of these, right? But what we want to do is say, I want some cow, that the body's here and the legs extend back to the beginning of time, right? Okay, so I know which particles are going to later rejoin. Okay. So, and break up under shear and so forth. So those are experiments we haven't, I'm not ready to share the data on that yet. Okay, but let me give you some sense of how this still starts to tell you that this technique can create them. So we have some data. And actually, I'll talk more about this same data set later, where we have a bunch of particles. And the black ones in this picture have a higher friction coefficient. And the red ones in this picture have a lower friction coefficient. And the way we did that was simply by wrapping them with Teflon tape. Okay, so very, very low tech. Okay, now, okay, so unfortunately, there's actually a funny reflection in the image here. So ignore the fact that it's brighter there. That's just a reflection. It doesn't affect the image processing. It's fine. So these red particles here are low friction ones. Can you see them over here? Can you tell in the force network where they are? They don't look particularly special, do they? Right? They just look like, you know, there's forces going through this. Okay? So what we'd like to see is whether or not this network community detection technique can tell who the low friction particles were. And we know the answer because, and this is not coming out on the screen, the low friction ones have been tagged with a fluorescent stripe. And so when we turn on the black light, we can see which ones were low friction. Okay? So let's run this experiment. Okay, and so here's some network measures. Okay, so the black lines are the ones that were the bath, that are high friction. The red ones are the small number of low friction ones. The top row is average community size. The middle row is average community strength. The bottom row is something we call sparsity, but I haven't told you about that, so ignore that. The left one is if we use the normal force network, and the right one is if we use the tangential force network. Okay? So again, I told you guys, it's your choice what you make your adjacency matrix out of, right? I could pick to put any one of those forces there as the weights, right? So if you wanted to distinguish the particles, should you use the subsystem from the bath? Should you use the normal force network or the tangential force network? The tangential shows a much sharper deviation, right, I think. Okay? It's not perfect in any case. We can tell them apart, okay? But there's different information in the two, okay? And it might make sense that the tangential force network is important because if you're low friction, you're not carrying much tangential force, right? Okay? And so you're going to tend to have smaller average communities. It's being partitioned up differently. Okay? So this is completely an empirical result, okay? But it distinguishes the two. Now, what I don't have, okay, so calculating Q, there's an extension where you add an extra term here for omega. What I'd love to do is make a network in which each edge carries both the normal and the tangential force, right? Carries both those pieces of information. So these are now vector edges. Okay. There's starting to be techniques for doing that. I haven't mastered them yet. Okay. So there's obviously here that you want to be considering both of these types of information. And if we just zoom in on just slice the same data but just organized a little differently, you can see that, in fact, if you look at the strengths, it doesn't really matter so much if you use normal or tangential. It matters a lot if you look at size. Yeah. Yes, I think it would be. Yeah. So we picked this data set because it already existed, right? So this is clever reuse of data. And because it provided a nice test case that by eye you can't tell which the low friction particles were, but the network methods have no trouble telling it apart, right? And so the information is there in the force network. Yeah. And so we are now moving on, and this is where Sid would draw his bullshit line, right? We are now moving on to say, can we use this to make predictions? If I know the community structure now up to step 7, can I make a prediction of what will happen in step 8? Where will the breaks occur? My hypothesis is they occur at the boundaries between communities, right? Right? Things like that. Okay. Sound propagation should be, happening well within communities and poorly between communities, right? So this gives you a set of hypotheses, okay, where just the network itself tells you a bunch of things about the system. Okay. All right. So let's see. We are at perfect. All right. So that's the end of the network stuff. So questions about that before I move on? Yeah. So what's the easiest global control? what's the summary? So I would say I've mostly been doing tool development up until this point, right? So learning how to, so a lot of what we've been doing is learning how to correctly set these parameters, how to choose the right null model, right? How to pick the correct, I mean, if you go to one of these sites, there's 100 different network measures in there, right? So what are the right ones that are even appropriate to use for particular things? So, so I think I would say that I'm now at the point where I now understand my toolbox. I know the difference between a hammer and a wrench, right? I know what each one's good for. I know what I can distinguish. And now's the time to start doing science. Yeah.
Two questions. The first is, how well does this work in 3D, where there are a lot more degrees of freedom? And the second is much less well-informed, which is, earlier in the school we learned about phase transitions that happen in community detection. Do you know where you sit?
I don't, because I wasn't here. So somebody who heard and understand should come talk to me at break or lunch and talk more about it. On the 3D, one of the really cool things about these network methods is they, to some extent, don't care how many dimensions you're in, because the adjacency matrix is only ever a 2D object, right?
Right,
but the sparsity and stuff will likely matter, right? And so whether or not the same choice of things like the omega stickiness parameter or the resolution parameter, I think resolution parameter will probably stay the same because that's about sort of the mean force. But this is a circumstance where I think it's really nice that these matrices are just 2D matrices no matter how many dimensions you go to. They get sparser and sparser, right? Which means I think computationally you're in pretty good shape, right? Because a lot of these operations are efficient the more, for sparse matrices. So I don't know a ton about the computational complexity that.
They get denser for a fixed number of particles because you have.
Oh right, yeah. So maybe it does get harder and harder then. Yeah, yeah. I don't have 3D data to work with. I would love to have 3D data to work with. And, some of you know I am trying to get myself 3D data, but so yeah, so that's a good question. All right. Jump forward here. All right. So now I'm going to talk about a set of tools, and I think Booble will probably continue to do more with some of the. No, you're not. Okay. Not doing any words. Okay, cool. All right. So we'll see how far we get. So more than 25 years ago, Sam Edwards had this idea, okay, and I really love this little quote from him. It's from the paper. If a powder consists of uniform salt cubes and is poured into a container, okay, one expects a salt powder of certain density, okay, and Sid talked about this. You can repeat the experiment, okay, and you get a well-defined distribution of values for a well-defined protocol, right? Clearly, a Maxwell daemon could arrange the little salt cubes to make a material of different properties, okay? But if you don't allow Maxwell daemons, right, there's some ensemble, okay, that generates for a well-defined set of macroscopic variables, and therefore there should be some sort of statistical mechanics-like approach that is able to make progress there. Okay, so here's the simplest example, right, of the idea. If you have a small system volume and try to put objects in it, okay, in this case it's crystalline, there's only one valid configuration, okay, but if you open the box a little bit and allow a little more room, right, okay, oops, now there are more possible configurations, right? Particles can be in different places, okay. So by changing the volume, you change the number of possible configurations. This gives you a configurational entropy, okay? And by analogy to thermodynamics, okay, there may well be a temperature-like variable associated with that.
Sorry, let me just make one comment.
Yes.
So Edwards was very specific about what ensemble.
I know. Jammed. I'm getting there. I'm getting there. I'm getting there. To the jammed configurations. I'm getting there. They need to be jammed configurations. Yes, I am getting there. And the hard spheres. I am getting there. This was meant to just give people a flavor of the idea. Okay? All right. So I'm going to make a little chart.
I guess the reason I'm pointing it out is this is how we define pressure in normal cases.
Yes.
So to distinguish between pressure and convexity, we have to restrict it. Long thing.
Yes, and I will get there. And you can jump in again if you think that I've left something out. All right. I'm going to make some columns here. Okay. So and I'll use these columns, I'm just not using them yet. Okay. So this is subject to conservation of energy. Right? So when you do ordinary statistical mechanics, this is what you count as valid states. Okay. Okay. In contrast, when we count how many states there are as a function of volume, okay, these need to be overjammed configurations of hard spheres. Okay?
Are we removing ramblers for this, or are we not thinking about
We're not thinking about that.
Edwards doesn't, because there's
Yeah.
no force concept here. So
Right.
ramblers are
Yeah.
no
Okay.
contact.
Okay. Now, because I've been leading you down the road with forces, you can probably guess what's going to end up in this column over here in a minute. Okay. But I'm not going to fill it in yet. Okay. All right. And you have some sort of entropy. Okay. Here, by convention, people have tended to leave out any sort of Boltzmann constant there. Okay. And this is purely configurational. Okay. And okay, and just as you can write this temperature-like quantity, okay, Edwards proposed to consider this quantity where this is called compactivity. Okay. Here's a way to think about it. Okay. At low temperature, what can you not, so T equals 0. Let's say T equals 0. So at T equals 0, what's true? You can't take out any more energy, right? Okay. You can't take more energy out, right? So what does that tell you here? At x equals 0, what can you not do? You can't compact anymore. Okay, you can't compact anymore, right? You've taken all the volume out that you could take out. Okay, so this corresponds to random close packing, right? Okay, so it maps onto stuff that we're familiar with. Okay, now there is, unfortunately, let's see, I'm going to continue this on another thing. Actually, let me bring this down. So Boltzmann says that all, this is an assumption, all valid states are equally probable. And I should note that's an assumption. Okay. Now, Edwards made the same assumption. But unfortunately, as Bubel and Don Frankel just showed, it's only true at jamming.
Which is precisely what Edward said.
Did-
Because that's the point where high spheres are
touching.
Soft sphere jamming point.
Is that,
The same as the ensemble Edward system.
well, but
The error that the community has
made is to continue that.
to compress systems where the soft
Doesn't-
sphere is over. The Edwards wasn't wrong, Edwards was right. Probability holds only at the point where spheres are
I-
touching, which is precisely what he was
Okay.
talking about block space and high spheres.
Those who have not met Bulbul yet, so we'll be singing also tomorrow.
I'm just saying,
Okay.
you can't put a,
Okay.
correct.
Okay. So,
And that's the paper.
so we'll just do this. All right. Only true at jamming. And again, for hard spheres. For hard, and I said that for hard spheres. Okay. All right. So C. Okay. So if it's only true at jamming, it's going to limit the utility of it. Okay. It makes it less powerful than the Boltzmann one. All right. And if you have e to the minus e over kbt, then you'll have something like e to the minus v over x showing up as factors in all the usual places. Okay, questions? All right, so I'm an experimentalist, okay? And there are people in the room who could tell you how to start counting the number of configurations, right? Okay, that's not something that's experimentally tractable, right? Yeah.
So are configurations, so non-isostatic configurations are valid hard sphere configurations, but they're not configurations.
Since that you want to be counting, yeah.
They're not jammed.
They're not jammed, so they shouldn't get counted.
But they're not jammed only in the sense of
In this very strict sense.
understanding the forces, right? You
Right.
can construct the packing, which
Right.
is
Or in the
hyperstatic.
sense of torpedoes jamming, where you can't move a part.
Well, but you can construct a hyperstatic hard sphere packing.
Sure, these are all for disorder. Right? Edwards is.
So I will say that there's a reason I'm leaving this column over here, because it's useful to consider the forces, right? And that column is so far blank. Okay. Yeah.
Can you explain the argument here?
So if your whole framework lies on the ability to count the number of configurations, it's very important you agree on what you're counting, right? So let's say how many students are in the room. Like I might say that everybody who signed up as a participant is a student. NSF might say we only wanted to count the grad students, right? If you don't agree on what you're counting, then you're going to disagree, right? So I think, and it matters if we, from an empirical standpoint, so this is the strict theory that was laid out, right? And as scientists, we test whether or not, A, its assumptions are valid, right? B, whether or not it even matters, right? C, whether or not we want to go back and adjust the theory. I mean, the scientific community adjusts theories all the time in response to what's observed, and so forth. And so the precision that Eric and Bubel and I are arguing about is what exactly the theory is. Okay? And Bubel wants to point out that lots of people have been sloppy, right? Okay, and she includes me in that, right? Okay, and only in the early days, I've matured. Okay, now I'm going to justify, and this is, I want to point out, and this is one of the reasons actually that it's really important to think about the experiments that you do. So every method that I told you of measuring forces depended on the particles being deformable, right? Right? Either it was an atomograph and they were deforming the rubber spheres and looking at the deformations. The photoelasticity depends on deformability. So any measurement that an experimentalist is going to make in the lab that gives you forces is already what? On this list, right? Okay. So why do I make measurements on particles that are deformable? This is why you look under the street lamp for your missing watch, right? Okay. You have to start the place that you actually can look. Okay. So there are compromises involved in this. Okay. And I would say that if this is going to be useful, right, I want to be able to try to use it on things, okay, for which maybe it's not strictly true, but may still nonetheless have some utility, right? Ideal gas law. Do we love it? We use it all the time, right? We use it all the time. Is everything we use it on an inelastic, non-interacting gas? Only in some approximation, right? Okay, and nonetheless, it does a pretty darn good job, right? You'd have to be aware, however, when you've gone past, you have to know that you've crossed the boundary, right? And that you should be switching to something that's a non-ideal gas, right? So delineating where things work, right, is a separate thing from where they're strictly true, right? And as an experimentalist, I'm happy with works well enough, right? It will help me predict something about some problem, and that may not make some of you happy, right? We may disagree on that, okay? All right, so how many of you know where you can stop using the ideal gas law? Eric?
Where you can stop using it?
Uh-huh. Where you should stop using it. Although we sometimes do, right? Okay. How about if as a gas gets hotter and hotter? Turns into a plasma. So if you start getting charges coming off, right, you should be worried, right? Okay. So we are aware, right? And people who do astrophysics, for instance, have to worry about this, right? Where is it okay and where is it not okay to use some particular theory? All right. All right. So, okay, where were we? All right. So I am an experimentalist, and I have no ability to count my configurations, right? And so you think I probably should have no business even walking down this route, because I have no way to measure temperatures. And so of what possible use to me is this theory, right? I need a thermometer, right? I need something that will tell me what the compactivity of my system is. And this might be useful, right? Right? I want to know for some system, you know, if being close or far from x equals 0 changes the properties of a system or some such thing. Okay? So I need some tool to do that. The what? Yes. Yeah. So if I'm going to go testing Boltzmann, you want me to have Avogadro's number, right? So how many particles have I shown you in my?
I think it was asking about
ergodicity. Yes. And what have I shown you? Okay. So let me handle that large N first. So do I have Avogadro's number of particles? No. So I've already got a problem even before I get to ergodicity. All right, how about ergodicity? What have I shown you so far that should concern you? Okay, they don't move that much, right? Okay, so these are athermal systems. They don't explore configuration space, right? So as an experimentalist or someone doing simulations, you need to introduce something else, right, to generate something like exploring parameter space.
Edwards is for a completely non-organic system. The way he defines an ensemble is through repeated experiments.
Right.
It is a non-organic because by definition it's a block state. It can't go anywhere.
So anything you
just repeat the way he said it. You tap it, let it rest.
do it again. And so this, and as you can see now, this very much inspired the experiments I've been telling you about, right? That this idea that I wanted to redo experiments, open the walls, put them back together, open the walls. And so some of these experiments operate, so the experiments I showed you earlier today were ones where we opened the box a little bit, right, so that we couldn't explore different particle configurations. In other experiments, we open the box all the way. We have a set of air hoses that sweep across it, generate a completely new configuration before we start up again. Okay? And so you need to, as the person doing the science, whether it's simulations or experiments, need to make decisions about how you want to explore the different configurations, right? And what I was telling you before was I was trying to fix the particle configuration and vary just the forces by itself. So isolating one of these from the other. Okay, so we are going to get nowhere near where I thought we were going to get. That's okay. All right, so first time that's happened? Excellent. Okay, so this is a lesson, and I think this is quite a general lesson, okay, that I'm telling you about in the context of this Edwards ensemble, but I think is a useful thing to think about in a broader sense. Okay, so histograms can be thermometers. Okay, and nobody would ever design a thermometer like this in the real world, but it's worth thinking about. Okay, and this is in fact how we do our experiments. So if you wanted to know the probability of observing some volume to the system, right, you'd have to know how the multiplicity changes as a function of the volume. You'd have to know the partition function, okay, and this would go into your Boltzmann factor, right? Okay, so if you do this, okay, so note that this is independent of V, and this is independent of the convectivity, right? So, and I've told you I'm an experimentalist. I can't count things. That's too hard, right? So this is unknown, and this is just as bad. Okay, possibly worse, right? Okay, so these are things I can't measure, right? So what? But if I look at a ratio, so I make two measurements. Okay, so what are my histograms of? So this is the histogram ratio of local volumes. Okay, if I look at this ratio, some things are going to cancel out. Okay, namely this. Okay, and so I'm going to get a ratio. Let me write this. I'm going to get a ratio, okay, where this part here gives me a relative gives you a relative temperature. Okay, and if you know where your 0 is, which we do know, it's at random close, all right, then we can figure out where we are. Okay, so this is a technique. There's two good places to get this. So one is an older paper, Dean and Lefebvre. This will be it's in the notes too, so you can get it from there. The PRL, and then the granular contest, Sean McNamara et al. There's a PRE 2009, okay, which is where I had learned about it from actually. Okay, but so this is a way that you can actually make a stab at doing that.
Just
yes.
you want to put X on the left-hand side on the P, because those are different X ones and X.
Oh, sorry. Where? Let's see.
The P of X and B.
Oh, yeah. Sorry. Yeah. Yes. The what? So I'm preparing a system at different volumes.
What happens to the omega V?
Ah, so this is independent of x. Okay, and so they cancel out. Okay?
No, so
That's what you.
no.
I said okay.
V1 and V2.
So you want me to write this out all the way?
No.
Okay.
It's you're right. The volumes have to be the same and x.
Oh, sorry. There we go. There we go. That's what I was doing. I was overzealous in my subscripting. Thank you for pointing that out. I was overzealous in my subscripting. Okay. 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 Overzealous subscripting. Thanks. All right. So we can do this experiment, okay, because we can generate lots and lots of configurations and look at it. And I just want to demonstrate that there's actually two predictions from this. So one is that I can measure a relative temperature. The other is I'm going to do that. This needs to actually fit this form, right? So a prediction of this model is that this is an exponential at all, right? Is there any guarantee that it's going to come out to be exponential when I do the experiment? Not in the least, right? Okay, so that's a testable thing. Okay, so the data I showed you earlier was, let's see, I'm trying to think here. If I got 15 minutes, how do I want to use it? I'll quickly do this, and then I'll fill in that last column a bit. Okay. All right. So the data I showed you before was actually drawn from this experiment. Okay. This was its original purpose. Okay. Was that this is work of my former student James Puckett? That if you had a system with a high friction and low friction part, would they even agree on the compactivity? Okay. And this is like sort of like a pre-zeroth law, right? If things don't come to equilibrium, it doesn't even make sense to talk about this as a quantity, right? But at the same time, we're also testing whether or not this method is even a good method for measuring things, these temperature-like variables. Okay. So we had these three lighting schemes, right, that we could work. Whoops. Thank you. You just crashed. That was not what I wanted. All right. So we had these lighting schemes, so we can detect the particles. I've overlaid a bunch of different kinds of data on the same image now. You can detect who are the frictionless particle, low friction particles, who are not. You can detect the forces, you can detect the particles, you can detect lots of stuff. Okay? And we can look at histograms. So here's some sample histograms, right? So here's the local Voronoi volumes. Here's one with a high volume. Here's one with a low volume. Okay? This is the kind of Voronoi where you draw a line between the two edges, not between the two centers, because the system is polydisperse. Okay? We have a bunch of histograms, and what I want to do is take ratios. Okay? Ratio between the dots and the triangles at each point along here. Okay? And if it's an exponential, okay, then I'll come out to have a straight line on a log-log plot, okay, which in fact we do. Okay? So this idea that it's reasonable to write something of this, a Boltzmann-like factor, checks out. Okay? All right. And however, if we go through and try to do the whole thing and say, how does it vary? Okay, does the convectivity equilibrate between the subsystem and the bath? Okay, and we've used the fact that we're changing here, but we're changing the global packing fraction. Okay, this is places where we shouldn't make the measurement. This is where places where we should make the measurement. Okay, and we can use the fact that we know that, in fact, x equals infinity. So for x equals infinity, that's random loose packing. Okay, so the point where it just becomes jammed. Okay, and at no point above that do the compactivities measured in the subsystem and the bath match. Okay, and this most recent result, that in fact the equiprobability fails, okay, above this point, is almost certainly the reason why we didn't get the rest of this to work out. Okay, so we didn't understand this until just last month. Okay, what was going wrong here? Okay, so what's left? So is this recoverable? Okay, I don't know, right? So it's broken. Okay, maybe we were foolish to try it. Okay, and it remains out there something that, okay, this system, a framework of looking at things, doesn't give us a temperature that behaves like a temperature. It doesn't even satisfy the zeroth law, so maybe we should stop, right? Okay, so that's one possible outcome of this. Okay. But I'm going to quickly say, so the explanation, okay, is this paper right here. Okay, so go check that out. All right, but we have more information than this. Okay, and in fact, life has moved on in the last 25 years. Okay, and people aren't only talking about the volumes; they're also talking about the forces. Okay. Okay, so there's a generalized version. Okay, go beyond this. Okay, where we want to count the straits as a function of some stress tensor. Okay, and everything I've been talking about until I started talking about this, I was telling you about forces, right? So I think the forces matter. I've given you guys tons of reasons why we should think about forces. Okay, and so this is where my thinking is lying. Okay, is that okay? We should also be looking at configurations as a function of stress. Okay. We can do the same thing, okay? But now this is configurations of something called the force moment tensor, which I will probably not tell you much about in the interest of time, but I will happy to talk to anybody about it, as would Booble, I assume. Right? And that there's a quantity called the angericity. And let's see, I'm going to call this is the tensor, right? And if you have some component of that tensor, there will be a quantity called the anger. This is terribly spelled. A quantity called the angericity, which so something terrible has happened here. What do you notice that's happened in the definition? The reciprocal has been lost. Okay? I apologize. This is not my fault. Okay, so people tend to, so this number has come to be defined without the reciprocal. Okay? Okay. What? Because of the tensor, and you would not want to be taking a reciprocal of a tensor. So this turns out to be a much better way to have done it. Okay, so now we need to redefine a little bit of what we mean here. So what does it mean? You guys, what does it mean when that equals 0? Yeah, or would you rather that I asked you this question? Which question would you rather answer? Because as Booble said, this is a tensor here, and so you want to be able to write. A hat, and we can't do that if it's in the denominator. Yeah. So this was so there was a very, very good reason that it got flipped over. Yeah. Yeah.
If it's infinite, isn't that similar to the t equals 0?
That's like the t. So this is the one you want to answer, right? And this means so this will be at first force transmission. So where stress first starts to exist in the system. Okay? All right. And so on and so forth. Okay, so this is where I have been putting my efforts these days. Everything I showed you over here, you can just change the variables. You can try the same things out. This force moment tensor, I'll show you what that is. So because we know all the particles are, and we know all the contact forces, okay, the force moment tensor is just the direct product. Right, so this is column vector times row vector. So AXBX, AXBY, right, so you get a whole tensor out of this. Right, okay, this is related to the Cauchy stress tensor. That's the normal boring one, right, that engineers love. Okay, you can take the trace of it if you want to get the pressure. You can get its normal. You can get its deviatoric. Right, so anything that in an engineering context would make people happy, right? This framework naturally connects to that. Yeah.
So like this is what Blumenfeld calls the contact zone?
So I would say that you could make another column here, right? So yes. So so I'm presenting you a subset of the ecosystem. Okay. And so he would say that there's a different quantity that involves the contacts themselves, and it's not the same as this, but it looks a lot. It has very much the same flavor. That you want to know, what the connectivity of the system is. Yeah. All right. So I'm going to not continue to tell you what we have learned about that, but suffice to say that you guys, on Friday, I showed you guys what happens when you load a system differently. Could you tell the networks apart? Right? Right? We have under compression or under shear. Right? Okay. So the distributions that you get over there are going to be different depending on the history. Okay? And it will show up in this formalism as well. Okay? So I think that this is allowing us a way to capture what we're seeing in experiments. Right? And I mean that in an empirical sense. Right? In an empirical sense, that this is actually representative of what we see in our experiments. And I will close there so you guys have time to ask me questions.
How would you want to measure that?
All right. So actually, I'll do it in a just completely algorithmic way. So the gray particle, I give you its coordinates. It's at pixel this, that. The one above it is at some other coordinates. So Rm minus Rn. So this is like the moment arm on that guy, right? So I know that vector. I know the vector for my force. I multiply the two, right? And then I add them up. And in fact, we do this over clusters of about 8 particles to get a little bit of averaging. You can go down as low as 2 or 3. It still works. 8 gives you a nice amount of averaging. But this is literally just a thing that you can calculate and which has a physical meaning. Right? This is the building blocks of the whole stress tensor. If you know the boundary forces, right, they need to match what this is. Right? So this is extremely physical. So the angularity itself, so let's look over here. And I'm realizing now the erasing is not a great deal. So I would replace volume with stress. I would replace convectivity with angularity here as well. I'd take ratios of histograms. Okay. And the machinery that I showed you for this works the same way. Right? It's and this is a very experimentalist way to visualize it, that it's a recipe. Right? It's an algorithm that I know how to construct. And then it's an open question whether or not that's useful. Right? It's an open question whether or not it satisfies what the theory is strictly supposed to be. Right? I think those are 2 separate things. Right? I think they're both very important. Okay? But like I said with the ideal gas law, something can be useful even where some of the pieces are slightly broken. Right? Right. And so I think it's still worth doing even if I've broken some of the pieces. Yeah. And there's a Boltzmann-like factor, and we will write that down. What do you guys want me to write here? Sigma alpha. Right? And I'll put the IJs on it to make it clear. These are parts of a tensor. Right? Yeah, so everything goes along the same way, except that you take the reciprocal. It's a capital sigma, yeah. Okay. Yeah, let me do that. I've been a little bit sloppy up here in doing that, switching between the two. Yeah. All right. Thanks. Coffee time.